Hi everyone, today I want to introduce our paper, Find Wrinkle on Coarsely Meshed Seashells. I'm Zhen Chen. This work is collaborated with Xiaoyu Chen, Danny Kaufman, Melina Skouras, and my advisor, Etienne Vuga. Wrinkles are everywhere during our daily life, but it is hard to simulate wrinkles efficiently. There are several classic ways to simulate wrinkles. One is to use mesh spring system, or FEM, on triangle meshes. For example, this dress is simulated using FEM with 80K triangles and 40K vertices. The key drawback of this approach is that you may need a high-resolution mesh to resolve detailed wrinkles. This will slow down the solving speed. An alternative way is to use adaptive refinement. That is, we adaptively refine the mesh on the wrinkle domain. This did a good job when wrinkles are sparse and sharp. For example, if you apply this idea on the same dress, you will end up with fewer triangles, but visually similar result. However, what if wrinkles are dense? Consider a case where you rotate a cylinder by 10 degrees. By rotational symmetry, you may expect a uniform distribution of wrinkle patterns. In this case, which parts of the mesh are going to refine? Adaptive refinement schemes will arbitrarily choose some regions to refine before others. This leads to a biased result. Also, as deep learning comes to our life, there are some approaches using this technique. They achieve some convincing results, but still suffer from several drawbacks. First, they need training data. Second, they cannot handle materials which are very different from those in the training data. Our goal is to predict complex wrinkle patterns on very coarse geometries. For example, we can predict fine wrinkles on the same dress using only 2K vertices. This is only 5% of degree of freedoms compared with the classic FEM solver. Then the question is, how can we do that? The key idea of our approach is to represent wrinkle shape by two parts: a wrinkle-free base mesh, which captures coarse level information, and a wrinkle correction, which encodes fine level details. You may ask how to compute these two parts. Let me first introduce our base surface computing scheme. One natural question is, what is a good base surface supposed to be? In general, it should capture the overall and coarse shape of wrinkle surface. One trivial choice is to use low-res FEM result. However, due to the locking issue, low-res FEM result already has bad and alias wrinkles. Adding wrinkles on this bad and alias geometry is not a wise choice, because it is much harder to figure out how to undo these bad wrinkles and put in the good ones than just adding fine wrinkles on a smooth base surface. Therefore, our ideal base surface should be smooth and wrinkle-free, such as the one on the right. We instead use tension field theory. The key idea is to ignore the compression part of the strain tensor. This will give us a convex energy and generate smooth and wrinkle-free surfaces. Notice that this theory is used in computer graphics when designing inflatable structures and skin tight cloths. Okay, till now we get the base surface using tension field theory. It is time to compute the wrinkle correction. To begin with, we assume that the wrinkle correction is a function of amplitude and phase field. For example, if you replace delta R by these two geometries, you can get the right two figures. Notice that the phase and amplitude patterns encode the important wrinkle information, and they are consistent with the leftmost wrinkle surface. Moreover, we point out some observations here. First, phase is a fast variable, which changes significantly within one wrinkle period. But at the same time, base surface strain, curvature, wrinkle amplitude, and frequency are slow variables, namely, can be treated as constant within one wrinkle period. Since our goal is to add wrinkle patterns on a coarse base mesh, the variational problem that solves for this should use only slow variables. Therefore, we replace phase by frequency when deriving the energy and doing optimization. After that, we apply a phase extraction step to get the corresponding phase information. I summarize the remaining tasks here. I will first go with some insight of how to get the wrinkle correction. Consider a semicircle as our base surface. One natural way to add wrinkles is to use a cosine wave along its normal direction. This will produce reasonable wrinkle patterns, but the strain is concentrated at the points where phase is equal to k pi. This strain concentration will lead to a non-zero internal force. In our paper, we derive some in-plane correction terms, which modify this wrinkle shape to fix that issue. See this green curve, for example. Compared with the previous one, the strain is much more uniform. To sum up, our closed-form wrinkle correction has three terms: a cosine normal correction and two tangent corrections, where the closed-form expression F and G can be derived by minimizing the elastic essential energy. Please refer our paper for more details. Once we have the wrinkle correction, we can go through the derivation of our reduced order elastic energy. To recall, our wrinkle embedding function can be divided into several terms: a base geometry term, computed using tension field theory, one normal correction term, and two tangent correction terms. Plugging these into elastic essential energy and coarse graining away all the dependence on phase, our final reduced order elastic energy is given as. This energy has four stretching terms together with two bending terms. Here we use Steinweiler-Kirchhoff material law, where alpha and beta are the material parameters. See our paper for more details. Let's look at the first stretching term. It has two parts: the base mesh strain and two rank 1 updates. These two rank 1 updates provide two ways to accommodate compression. One is the actual wrinkles. The other is the oscillations in amplitude. But the layer one is strongly penalized by the WS4 term. These two terms make sure that the compression is absorbed by the actual wrinkles. For the WS3 term, it basically says that the change of amplitude is perpendicular to the wrinkle direction. This can be seen in this stretched sheet example, where the wrinkle creases have near constant amplitude. Our final stretching term is the WS2 term, which penalizes the curvature of wrinkle creases. Please refer our paper for more detailed discussion of these terms. The remaining stuffs are the bending terms. The first bending term is the base surface bending, which encodes the curvature information of base geometry. The second one says that bending prefers high amplitude but no frequency wrinkles, if possible. Then, the final wrinkle frequency and amplitude is a trade-off between stretching and bending. The next step is to minimize the energy, and get the optimal amplitude and frequency. Instead of unconstrained optimization, we propose several constraints. The first one says that the amplitude should be non-negative. The second one means for any point P, is either wrinkle-free for the regions with no wrinkles, or curl-free for the wrinkle regions. In this way, we can easily extract our phase patterns. The final remaining task is to extract phase information based on the frequency. Thanks to the curl-free constraints we have in the optimization, this step is super easy. By just integrating up the frequency fields, we can get the corresponding phase patterns. To sum up, we first use tension field theory to get wrinkle-free base surface. Then, we minimize the reduced order elastic energy to get the optimal amplitude and frequency. After that, we extract the corresponding phase information. The final wrinkle shape can be computed by loop upsampling the base mesh and wrinkle variables. We tested our model on a variety of examples. For instance, we first try with draped garments. We get quantitatively similar results to the classic FEM solver with only 10% of degree of freedoms. We also succeed to reduce number of vertices by 1 order of magnitude and get visually similar results on inflatable structures. Furthermore, we verify the accuracy on well-studied cases. For example, in this case, a rectangular sheet is stretched from the boundary. Our method agrees with the numeric results mentioned by Wang et al. Compared with the other solvers, we use much fewer degree of freedoms. Our results also agree with the sharing sheet physical experiment. Again, we use much fewer degree of freedoms compared with the other physical approaches. We summarize number of vertices and total time comparisons here. Notice that among all examples, we succeed to reduce the degree of freedoms by 1 order of magnitude and achieve over 17 times speed up on average compared with the classic FEM solver. In summary, we propose a lava model to represent fine wrinkles on coarse geometry. Compared with classic FEM, our method decreases the degree of freedoms by 1 order of magnitude and achieves visually similar results. To finish up, I want to point out some future directions. First, currently our approach is a static solver. Extending it into dynamic simulation is an interesting future work. Second, our current approach only considers the condition when computing base surface. An overall contact and friction model should be proposed in the future. Third, we should consider more general wrinkle models using near-hooking materials or use different wrinkle bases. Finally, we seek to apply our approach for inverse garment design. Thanks. You can check our source code here.